Okay, guys, can we start? Welcome everyone. This is our second presentation. Today we will speak about deep learning and machine learning with MATLAB. I'm Daniele, he is Alberto, my colleague. As you probably know, we are the MATLAB student ambassador for Polytechnico of Milan. I start with a little bit of an introduction on our role here in Polytechnico. We are actually the link between MathWorks and Polytechnico. So we will organize events like this one on particular features of MATLAB. And of course, as you probably know, we have a Facebook group where each one of you can share his doubts or some suggestion on our work, and everyone can help other people. So we want to create a community. For this reason, I invite you, if you hadn't already done it, to subscribe to the Facebook group, because we need you. We need the major numbers of people, of course. So today we will speak about deep learning and machine learning, but I want to present you today's agenda. First of all, we will start with a little bit of presentation of MATLAB. Of course, I won't bother you with obvious things, so it will be very quick. After that, we will show you some basis of deep learning, because of you are from very different bases, from very different knowledge. So we have to give you some basis on which we can build our today's seminar. Of course, maybe some of you will be bored of these very easy notions, but of course we have to give some basic of this argument. After that, we will present you a problem, because we want to manage this lesson not only from the theory part, but we want to solve an actual practical problem with you, with different approach, of course. So problem presenting, and after that the problem solving. So I said with different approach, so from easiest one to the most complex one, and of course we will understand and analyze the difference in computational requirement, but also in the performance of this approach, and we will choose the best of this one. After that, we want to show another analog topic, that is the use of pre-trained network. As you can probably imagine, there are lots of big companies that are building their networks, and so we will show you how to modify this already trained network to work on your problems. And after that, there will be, of course, the challenge to win our beautiful prize. I hope you will enjoy it. So I start with a little presentation on MATLAB. What is MATLAB? I hope you already know, but MATLAB means matrix laboratory. In fact, is a programming language based on matrix calculus. For this reason, it is of course used in the most part for MATLAB analysis, for math analysis and the language. But during years, of course, it has become a very complete language. So with the use of the toolbox that are special add-ons that you can install for your particular use, you can expand the potentiality of MATLAB in every way. For this reason, it's very used in lots of different topics, and the strength of this approach is that is a unique workspace where you can do lots of different things, but all of these are linked and are interfaceable, so you can link the different parts between them. So now I want to show up only a little one add-on that I said you about. This is the hardware support that we will use in the next seminar, not this one, but it will be very useful in next. It is the possibility to deploy your code, your MATLAB code, into a hardware board. For example, Arduino, Raspberry, and so on. Why it is so important, this part, is because you can see your realization, your project effectively deployed on hardware. So I think it's quite interesting to see how you can really create a project from start, the programming part, to the end, so the realization, the physical realization. And the physical realization will be one of the topics of our next seminar. But today we are speaking about machine learning. So I give the word to my colleague that will give you some basics on this.
Good evening. Well, let's start about speaking about machine learning. We have to understand what are machine learning. So let's start from the definition and from what are the topics involved in the definition. We spoke about brain, statistics, data, and coding. So let's see how these things are related together. Okay, let's read it together. It's a field of artificial intelligence, okay, that uses statistical technique, so brain and mathematics together, to give to a computer system the ability to learn, to understand pattern and link between some data, of course from data, without an explicitly programmed. So the goal of machine learning is to build a program that is that can understand which is the relation between the data that we give in input. Okay. So the important thing is, we said relation, but of course a computer doesn't know what it means relation. What are the important things in the data? They see a lot of numbers, a lot of values, but he has to recognize what is a pattern. Okay, so we use artificial intelligence. So let's see what is artificial intelligence. A neural network, so artificial neural network, is a series of algorithms that involves and recognize underlying relationship. So relation that isn't so trivial to see. If you see a series of data, you probably see a relation, but a computer doesn't see which is the relation between the different data. So it needs to see which is the common structure in this data. Okay, in the set of data, through a process that mimics, so simulate what does the human brain. So we want to transmit the ability to learn that is strictly related with the human brain to an artificial brain. Okay, this is the zero step of the artificial neural network and the machine learning. We want to transmit our ability to recognize pattern to the computer. Then, how this process can be done? Of course, we have to develop an algorithm to start develop this model. Okay. So what we need to learn in general, we need images or some data, of course, some input, and a label. So the name of what we are going to put inside. Okay. So in this case, each image here, so it's a car, has the label car. Okay. Together, this will train the model. So fix the parameter to have the model that will understand if inside the car there is or there isn't, inside the picture there is or there isn't a car, okay? And then, when we have trained the model, we will go in the application side of this model. So we want to use this model. We pick a new image that we don't know if it's a car or not. In this case, of course, you have all understand it's a car. So we pass the image through our network, and the result is yes, it's a car, or no, it's not. So in this case, it's a car. Okay. This is again the basic of machine learning. And the label here in this corner you will see a little bit of we can say glossary each slide. Here label is this name, car, no car. So in this case it's a classification. Yes, there's a car, no, there isn't a car. But we have to start going deep inside what is our training algorithm. So in general, training algorithm procedure is we take the image with the respective label. We put inside the image inside the network, so the model, and we use the car, so the label, and use it inside the training algorithm. The training algorithm is a series of parameters and equation that will understand if what is the input data is or isn't the requested one. So we put inside the image, use the label in the training algorithm, we classify it. If the predicted label is the equal one on the one that is the one related with the image, okay, the network is going well. If it's different, so the predicted label is different from the car, we will fix the parameter to perform the next time a better recognize. Of course, this is a process that works with a lot of images, a lot of inputs, a lot of data. Okay, so you have to think that this is only a picture, but we can have there like 1,000 images and lots of and over. So better, more image you have, better will be the training. Okay, and so we do the training of the network. Going on, as I said before, we can use the network to predict which is the label. So we take the image, we pass through the training network, and we get the prediction. So the label of the image. Okay. So the prediction is classified an unknown image. Okay. We use the image inside the model, and we get the label of the image. Of course, this works if the network is trained correctly. There's some question about this first part. I'm quite clear to explain. Okay. Let's go on. We start speaking about machine learning. Machine learning, we can say, is the biggest topic of neural network. Machine learning is the basic structure, and it's composed by some mathematical equation that is called, in this case, neuron. And neurons are, of course, can be mathematical equation like this one. So this is a neuron that is the neuron is the structure. And in this case, with this equation, it's called the linear perceptron. Okay, and as you can see here, we have an input like x1, x2, and going over. Then we have a series of parameters y1, y2, and again. And then we have an output, so it's true or false. Okay. This is the structure of our neuron. And in a general machine learning algorithm, we have a lot of neurons, so a lot of these mathematical equations. Then, after speaking of machine learning, that is the big topic, we have a slightly more small topic that is called deep learning. Deep learning is, of course, a field, and it's called deep because it has a lot of hidden layers. But the question is, what is a layer? A layer is a series of neurons, in this case, you can see here in column, that does the same things. So we have here a series, a layer, that has that is an input layer. Here we have a series of layers, 1, 2, 3, that is hidden layer because does something that the output, something that is hidden by the network, because you see the input and the output, you don't see what is doing the network, okay? And then, of course, the output layer. So, deep learning is a field of machine learning, not different things. It's the same thing, but is slightly inside the big topic of machine learning. Another question should be, why in this year we are speaking about machine learning, and why before we doesn't speak about machine learning or deep learning in general? Okay. And this is the motivation of this answer, the answer of this question. Okay. As you can see, in 2010, with the error in general, it's about 30%. And then they slightly decrease, since this data is from 2015, and we probably go down again in the error. And of course, we pass a line that is very, very important, the human accuracy, because we can see here that, of course, the error in blue is the error that does a generic machine learning procedure. Okay, so we reach about 5% in general, and the human accuracy is about 7.5%. But what does it mean, human accuracy? Human accuracy in this case is the accuracy that has human performing a task repeatedly. So let's do an example to better understand. If I take 1,000 images of a car, if I give you this image and I say, classify if there is an image or there isn't an image, you probably do an error that is 7.5%. So, of course, I give you one image, you probably correctly divide if there's or there isn't a car. But in a big number of images, you have a general error that is about 7.5%. Okay. So our deep learning network is better than you to classify image. Okay. Let's go on. This is a little recap on, again, on what is deep learning and what is machine learning. Let's start from machine learning. We have, again, a series of inputs, okay? Some mathematical equations, some neurons, okay? The structure of the net that recognize some relations, some pattern inside our image, and then with this relation is the thing that is a series of neurons highlight. We are going to proceed to the classification. So we decide if the image that we are giving to the net is, in this case, a car or something else. Okay. And now we have to see what is the difference between the deep learning. In deep learning, we are giving, again, a series of images, and then we have a series of hidden layers, lots of hidden layers, that does a procedure that's called feature extracting, learning features. Okay, so it again highlights the pattern, and then with a series of mathematical again function, it will highlight if there's in the image that I give a pattern that recognizes if this is a car or not. Of course, they both use mathematical equation, but different is this one use equation like with a vector of information. So we have to put inside our machine learning a series a vector of information. In this case, machine learning can handle also 2D vector, so a matrix of information. Okay, this is the we can say one of the difference between these. Okay, so now after this introduction, we can start go deeply again inside what is the general workflow of a network. We have the data, so images, database, or sensor. With sensor, I mean a series of data. So like a table of Excel containing the pollution of Milan of the past 2 years. I don't know, some data. Okay. Then with this data, we have to perform a process that is called label and process process data. So we have to handle this data and modify it to have the best data to fit inside our network. In this case, as you can see here, we have a picture of a plane. We have to resize, to do a transformation. We have data augmentation, so take one picture and flip it. So have 2 pictures mirrored. We have to label this picture to say this is a plane. Don't be sure that what inside the picture is it's correct. This is an airplane, of course. I don't know how to explain again. Then, after this step, we are going to perform the so-called developing predictive models. So we have to design the architecture of our net. We have to tune our hyperparameter. Then I know hyperparameter is a new word, but don't worry, we will explain later how it's a hyperparameter. And then we have to perform the training network. So we have to do the learning, to give the image to the network, and then the computer has to work to analyze all the image and give our model. And then we have the last part of that is validation and confusion matrix. So we have to see if our model is working well or not, if it's pretty correct or not. And then, last, of course, when we have this model, we have to use it in our hardware. We have trained the model, we have to use it to do what is the purpose of this deep learning structure, this code. Okay. So, after this, again, workflow, okay, we can see that is numeric data, time series. So this is should be a sound wave. You can take a sound wave and then use it to perform a training. If you want to, I don't know, recognize pattern inside a song or some also other stuff, noise inside there's no restriction of the topic on which you can work. Okay, text, images, okay. We can now see this is an important process. This is the process that takes the longest time in your building of the network. Because if you start from images that are not already prepared, so it's not resized, it's not fixed to your net, you will do this by your own, so you have to perform an important color correction. Let's suppose that you have an RGB image and you need a grayscale image, or you have maybe you work in a hospital and you have X-ray image from a scanning of something, and you have to correct the color to highlight which is the important thing inside the image, or I don't know, other stuff. And then you have to resize. If you take a 5 megapixel image, you probably can't use it inside your network. It's too big. You have to resize to the part that is the important part of the picture. Then, if you are thinking to use machine learning, you have to do this operation that is called flatten. So you take the 2D array, the image, and then you split it inside a vector, so you can use it inside machine learning. And again, as I explained before, data augmentation. You can take your image, flip or mirror it in some way that you can have from one image like 4 images because you flip it, you mirror it a lot of time. And then this part, image data store. Image data store is a very specific feature inside MATLAB because it can allow you to handle lots of the image, so a big database of images in a way that doesn't require too much power on your computer. So it doesn't move anytime you call the image, all the database around your memory, but you use like a pointer, a structure that is not a pointer, something a little bit more complex. But to better understand this, we will see this little video.
So far, you've been importing each image into memory individually and then using AlexNet to classify it. That's great for 1 or 2 images, but in practice, when you're doing deep learning, you're working with tens, hundreds, or even thousands of images. In that case, a better approach is to use a data store. A data store is a MATLAB variable that acts as a reference to a data source, such as a folder of image files. When you create a data store, MATLAB looks at the files and stores some basic meta information about the data, such as the file names and the formats. But it doesn't import the data. Instead, you can use the data store to import the data later when you need it, either individual files or the whole data set. CNNs in MATLAB work seamlessly with image data stores. You can get AlexNet to make predictions on a whole collection of images by providing the data store instead of the individual files. You don't have to import the files yourself, which is more convenient, and also means you don't have to worry about managing your memory. MATLAB will read the images as it needs them, so you don't end up with 1,000 images in your MATLAB workspace. In this section, you'll create a data store and use it to see what AlexNet predicts is in each image in the collection.
So, that little video explained what is an image data store. It's clear? Okay? Since here it's clear what I try to explain to you. Okay? Some question? Can we move over?
Yes.
Okay. Let's start talking about again machine learning. We have the 2 types of machine learning. We have perceptron or k-nearest. Perceptrons allows us to divide our space into 2 parts. Like in this case, we have dogs and cats. With a perceptron, I can draw a line that divides in which part is image of dogs and in which part is image of cat. So we can have like here, then of course lots of images fix the line in a better way to divide the 2 categories. And then we have the k-nearest. K-nearest is again a type of mathematical structure equation that can divide our space in these areas. So each area means that, as you can see here, the point is the data that we give to the network. And in the blue, like I write, it's the general pattern of this image. So if I get a new image inside the blue one, the blue area, probably it has a blue type. So it's a blue, I don't know, blue means cats. So if I have an image here, it's a cat. Okay, this is the 2 type of machine learning that we are going to use is later with the values. Okay, and then we have the deep learning, and deep learning uses a mathematical operation called convolution. And convolution means we take an input, we use a convolution mathematics, so it's like a mathematical equation, a mathematical structure that perform some type of stuff with a filter and your image. And just see which is the structure. So you have the input, the convolution, then a structure that reduces the dimension, then again another convolution, then again another pooling that reduces the image, and then we have the last part that is called classification. Okay, so we have this part that is called feature learning. So we highlight the feature inside our image, and then we go to a part that is called classification that does the job of deciding in which categories is our input is the correct one. Okay. And we have now to deal with this problem. One big problem: overfitting. Overfitting is a problem that common machine learning and deep learning is a problem that any type of network has. And to understand this problem, this is the right picture. We have here some blue dot and some red dot. Okay, if we perform a learning that build a model that divides perfectly the two images, the blue dot from the red dot, we build this green line. But as you can see, it's a complex line, a very complex line. So we said that it has learned too much. So it has learned too much detail of our model, our training image, training set of data. So we have the problem that if we are going to give to this network an image that is slightly different from the one that we use to classify, to train our network, it probably misunderstands the image. Because if the image that I give it is here, of course, it's perfect. If the image is here, of course, it's perfect. But if I give an image here, we can say in the gray part of this, where it's not defined if there is blue or red, so we don't have a generalization of our model. Okay. And of course, generalization means the black line. The black line that is clear and smooth and divide the two, the blue and the red, with some error, but is the clearest one. Okay. And the clearest one, how can we understand if we are going to do overfitting? Because of course we don't see this graph. This is only a demonstration, a picture to show you an example. Okay, we can understand if we are going to do overfitting with the loss. Loss is the error on data labeling. We take our set of data. Okay, we divide it into the training and the validation. The training is the data that we give to the network, and they will perform the training, so the featuring of the parameter of the network. And then we use a small set of images that we have take apart to understand if we are going to perform a overfitting. So we are building this green line. If the training is performing well, so it's decreasing, but the validation is not converging, so it diverges. Okay, it goes, it doesn't converge. It means that we are going to do overfitting. I know it's a topic not so much easy to understand. You have to see later with the example and then best understand what I mean with this type of graph. But the important thing is that if we gave a network too much, we perform a training too much specified on the image, we are going to have a network that won't perform great.
So we have to analyze how to reduce overfitting. Here you can see three different techniques to avoid it, and let's start from the first one called the dropout. Dropout is a procedure that allows us to switch off some neurons inside the net and And so take an easier one, as you can see in the B figure. And what is the purpose of this technique? In practice, we want to best learn the remnant neurons, so the ones that are functioning. So to do this, with the dataset, we will better train this neuron, because we are giving much information to each neuron. But when to the next iteration of the learning procedure, we will switch the type of neuron that are switch on, so they didn't become too learned, so they don't became they don't create overfitting. The second one is the regularization. That is a technique that allows us to put inside our mathematical equation a penalty, so something that reduce the value of our function if it will diverge from the one that we are doing with the training data. So let us assume that this one is related with the validation. If the validation and the training are diverging, this term will increase, and so it will tell at our network that is performing bad. And then we will use the last technique. It's called increased dataset. So what does it mean? Easily, it means we need more images or more data. So this is one of the solution. Not always possible, of course, because if we have a small amount of data, we probably can't achieve new one. We can't get new one from our let's say phenomenon, but we can, if we can, this is also a possibility. And going on, we can see we can start talking about training option. Training options are very important in our training procedure, because they characterize how the train will be trained. Our net will be trained. So let's start. It's the first one to choose, and the most important one is the algorithm. Of course, we have a lot of algorithms. These are three main, most important, and they perform well in each case. There's a slightly small difference, but now for our purpose we can choose Adam one. Then we can choose also the initial rate. So how long is the step of our network? So how long is the step of our learning procedure? Okay, so how fast will the net converge to a solution or to the minimum? But to better understand this, we will see a little video after. Then we will choose also the max epochs, so the number of time that our net will see all the database. So as you see, default is 30, and this is a big amount of time if our dataset is big, or a small amount if our dataset is small. So it depends. Probably it's better to set this value. Then the validation data, they are very important, because they allows us to see if we are performing overfitting or not. And to do this, we need also the validation set. And also we have the execution environment. So we can say the environment in which our training will be built. So let's do a little example. Using the CPU, we will maybe have a fast processor, but less core, so we can't parallelize a lot the learning. With GPU and multi GPU, we can obtain a highly parallelized operation, so we can in general achieve a better performance. And then last, the training process. So this option allows us to see how well is performing our net with a graph. And the graph we will see it after this little video.
You've trained your network and evaluated the performance. Now what? If the performance is good enough, then congratulations! You've made a network that can be put into production as part of your whole application. But often the results you get when you first train the network aren't as good as you need. So what do? Remember that the train network function takes 3 inputs: the network, the training data, and the options for the training algorithm. You can change all of these to see if you get better performance, but you're generally best starting with the options. The learning rate and momentum are the 2 key parameters that affect how the training algorithm updates the weights. Recall that the goal of training is to minimize the loss function, which is a measure of how badly the network performs on the training data. A common way to visualize the training process is to imagine that you're trying to find the bottom of a valley. The height of the ground is the value of the loss function. Your north-south location is one weight value and your east-west location is another. Of course, real networks have thousands of weights, not just 2, but the principle is the same. The gradient descent algorithm works by looking at the height of the ground at a few places around your current position and using that to figure out the gradient or direction that the ground slopes down the steepest. Then you simply take a step in that direction, which brings you to a new set of weight values. But how big a step do you take? The size of that step is the learning rate. If the learning rate is too small, you'll need to take a lot of steps to get to the bottom, and that takes time. But if the learning rate is too big, you might end up jumping around all over the place. If your weights have blown up and your network is giving terrible performance, or even not working at all, the first thing you should do is divide your learning rate by 10 and try again. Gradient descent with momentum tries to stop the jumping around without having to take really small steps. You start off going straight down the direction of the gradient, but at the next step, you don't completely change direction to the new gradient direction, but instead you turn toward that direction, similar to the way you would if you were a mass traveling in your original direction, but now being pulled in the new direction by a force. Your next step is therefore in a direction that's a weighted average of the previous direction and the new direction. That weighting is set by the momentum option. A common problem with all machine learning algorithms for supervised learning is overfitting. This is when your model does well at classifying the training data, but performs much worse on the test data. What's happened is that you've learned the details of the training data set rather than the general patterns. One way to prevent this is to use some of your data for validation. During training, after you've used your training data to update the network, test the network's performance on the validation data. Keep training while the performance continues to improve on the validation set. But once that performance starts getting worse, stop the training because you may be starting to overfit. Use these options to use validation during training.
So, as you can see in this video, we have see in practice what mean the learning rate and how we can visualize um, what is the procedure to converge to a solution. And in practice, we don't see this type of graph. We can see only this figure. This figure show us in the first part the accuracy. So how well is the prediction of the model? How well is performing our network? And the second one is the loss function. So a graph that show the error made to each sample and training. So if, of course, the performance of the accuracy will increase during the procedure of our training, and the loss will decrease and tends to 0. And in the right down corner you can see the legenda, and then you can also see some parameters related to the training of procedure in the data on the right. Of course, the important one is that with this graph you can highlight and see if we are doing overfitting or not by watching on the loss function and see if the dotted line is diverging from the orange one. Okay, another type of we can say of result of our net to better see if it performs well is the confusion matrix. The confusion matrix enable us to understand if if our net will correctly classify the image, such as you can see here, we have from left the true class and from the bottom the predicted class. If of course in each square of this matrix there will be an image. If they stays on the diagonal, it means that the predicted class correspond to the true class, so it means that is a correct prediction. If not, so they are out of diagonal, it means that are not correctly classified, so it will be a misunderstanding. And so this allows us to know how is the performance of our net, and also where our net is not performing well, so we can fix that type of input. And then last of our general workflow, we have the coding of our net with this particular toolbox called MATLAB Coder, and then of course the other one is the Simulink toolbox to code, and they allows us to do the to prepare our network to deploy to some target hardware, such as Raspberry Pi or a cell phone, or like the pictures, and some other stuff like a computer with specific OS. And then after this we will start talking about the problem definition. Problem definition, that is the goal of our presentation of today. So we will speak about the smart crossroad. Smart crossroad, like this one, it's composed by two streets with 4 lights, and the important thing is to understand if there's a coming a car to the cross. So like you can see in the right scheme, we can know if there's incoming a car, and we have the red. If there's a car in the other direction, it will stay the red, so the other car can pass. If it not, the light switch automatically to green, so allows our car to pass easily from the crossroad. This is a very important we can say application of our net, because allows us to do different things, so have a better I can say management of the traffic, of course, and then also we can reduce pollution due to the unnecessary stop of the machine at the red light. And how we can solve this problem?
So we stopped in this point. We have divided the problem in 2 parts: the cars recognition and the actually change the traffic lights. That, as I said, will be the next seminar topic. So let's focus on this first part. We have an image like this one of a crossroad. As you can see, there is lots of different items, cars, but also traffic lights, people, and other objects. We want something, now is undefined, of course, that recognize if this car have some, if this image have some car inside or not. This unknown point will be or a machine learning algorithm or a deep learning algorithm. Now we will see the two different approaches, and we will analyze the difference in these two different approaches. But let's start from the traditional approach to traffic management. Normally, what is done is an analysis of the crossroad. So we compute a statistical estimation of how many cars, how many people cross the road. And so we can estimate, of course, the number of cars and so on during time. After this estimation, we will deploy if either there is car or not. So if I'm waiting at the traffic light at the crossroad, I have to wait in every case. So our new approach, our modern approach, want to solve this problem by a iterative way. So first of all, we will collect the image of our crossroad because of it's better to have image that is it represent the actual situation. So, for example, we can put a camera on the crossroad that we want to develop and collect images. Maybe 1 month before the actual deployment, we collect lots of images at any time during the day. And to do this, we have a complete data set of image with car and without car. Once we have done it, we design our net. We can decide some type of architecture. It's not mandatory, of course. We train it, and the next step is the validation. So, of course, we can't deploy the net and see if it's working in the real case with the risk that some people can hurt himself. So before actually link the actual switching of the traffic light with the net, maybe we put our camera on the crossroad, and with a computer we can check if the net is predicting well or not our images. When we are sure that the net is performing well with a certain type of accuracy, we can deploy our software, our algorithm on the hardware that manage the traffic lights system, and so our net work real time. And when a car is approaching the crossroad, if there are a car in the other side, you can change the light. So the first step, as I said, is the training of data, the collection of our training data. Of course, as I said, the ideal situation is to take directly in place the data. So we put a camera on the crossroad, we take lots of images, I don't know, maybe once every minute and so on. But of course we can do it for day-to-day lesson. And so we take it from web. Actually there is this site that is very powerful for this purpose. This is called ImageNet. It is actually a neural network that perform image searching in all of the web. You can for example, type car, like in this case, and it search, look for car in lots of different sites across the net. So once you have taken this image, I can assure you that are very full of crap, because of course you download lots of images that is not car, is not nothing. So you have to eliminate, of course, the corrupted images and also all the images that aren't coherently with your purpose. So it's a very hard work, because you can give this task to a computer, you have to watch the image and see if there are some problem. Of course, after that, if we have a set of images that are quite correct, so there is car, there isn't car, but it's not outside our topic, we have to reorganize it in folder that classify them. So in our case, we we classify that image in some images that have car inside. So there will be a folder with the label true, that means that there is a car in the image, or false, that is images that aren't that in where there aren't car. Of course, a problem in these steps is that if I feed the training network with image of car and image of crossroad empty, so without car, my net understand and trained in a way that is not completely correct. In fact, imagine that the net see only car, so an object inside the image, or an empty crossroad, so it's like nothing. The problem is that if once I've trained the network with this set, if I put an object that is similar, is not similar actually to a car, but is an object in some place, it will recognize this object like a car, because if the net has not reference, it can't understand if it is a car or simply an object different. For this reason, we have to feed the net also with lots of images of different type, like person, animals, object, I don't know, lots of things that can appear actually in a crossroad, and label this image like false, as a false classification. In this way, the net understands not only what is a car, but also what isn't a car. That is main importance, because it's not true that whatever is not a car is whatever, or a car or nothing. You have to understand this specific point. Once I have this set of images, that is actually lots of work, I actually write the MATLAB code to import these images in my workspace and resize, make the data augmentation like Alberto explained you before, and all of the steps that I need to take my image from the basis to the two images that are ready to feed my net. So we want to start from the machine learning approach, so the easiest one. Alberto already introduced you machine learning, but of course we want to give you some best and more deeper focus. First of all, machine learning works on an equation. This is the perceptron, is only one type of machine learning equation, but how the algorithm actually works. As you can see, it's a normal equation with x1, x2, and so on, that are the input that we give to the net, to the model, sorry, and other parameters that are w1, w2, and p, that are the so-called hyperparameters. We have already told about this, but are the parameters of our net. So, during the training process, our training algorithm that are at this point only a black box. We can't explain to you also how it works, but to better understand this is the training algorithm change a little bit this parameter W1, W2, and P, making possible to give a correct labeling. So what I mean, I take an image like this, say 64 pixels for 64. I have to flatten it because machine learning algorithm take vector, not image. So take a series of data. In this case, this image has 4096 characteristics that are the values of each pixel of the image. These characteristics are inserted in this equation. If the result of this equation is a measure of then B, the results will be true. So in this case, it's a car. If it will be minus then B, it will be false. Of course, this parameter has to be changed because otherwise we can't do this computation. So the training algorithm takes a picture, hypothesize some initial parameter that aren't, of course, the true one, and it check the output. If this image that we feed is a car, we expect this output to be true. If not, actually what we can do is changing a little bit all of this parameter and retry. It's actually very simple. Of course, the mechanism on which that the training algorithm used to change and tune this parameter is not so easy because of course, otherwise it don't converge to our results. But this is the main idea. So I take the picture, I feed, I change the parameter, and I see the results. It's quite simple. The linear perceptron is only theoretical because of, as you can see, is a discrete function. So it can be or true or false, 1 or 0. What is the problem with this type of equation is that if the training algorithm tune a little bit all of these parameters, I can see a big change and not a continuous change. So I can finally tune all of the parameters. Because if I change a little bit W1, maybe I can pass from 0 to 1, and it's not correct, of course. I want to train the network changing a little bit the parameter continuously. I can see the actual effect of my training. So actually, it has we use different type of activation function, like this one. This is the sigmoid. As you can see, this is a continuous function. It's better because if I change some parameters a little bit, I can see I can see how the results change. So with a little change, I can see a little modification of the output. And so the training algorithm perform this change, and of course, once I've reached some level of accuracy, I stop the training because I'm satisfied with my machine learning algorithm, and I stop here. This is only one of the activation functions. Of course, there are a lot of these, but this is the actual how it works actually. I want to show you also what it does in practice perceptron. Suppose you have only a 2D problem. So you have some items that are characterized by two features, x1 and x2. For example, we can think of x1 like the area of the symbol. So in this case, minus have a minor area than plus, of course, because it is smaller. And the x2, we can think about it as the height of the symbol. So as you can see, minus, of course, it is slightly different between each other, but are of course in this area of the graph. So with minor area and minor height, the plus will be on the other side. What we can see that the training algorithm actually hypothesizes a first line. That is not correct, of course. And during training process, I change these values, W1, W, and V, according to the minimization of loss. So during training, I change this line in a way that I can divide the space exactly in these two different areas. Once I've done it, I reach my result. This is the best result I can reach. So once I have this line, my machine learning algorithm is trained, and I can perform classification. So I put another item inside. In this case, is this dot, unknown dot. As you can see, this unknown dot will be two characteristics. This x1 of the dot and this x2 of the dot. So I can put this dot here. Of course, you can understand very well that this will be classified as a double class because have characteristics similar to the other classes. And this is how the machine learning does in practice in very high representation. But this is not the only type of machine learning approach. We have in fact, this is actually the command of MATLAB to use this different type. Linear discriminant is the perceptor, you can see, and the quadratic discriminant is more complex, but can perform a very most complex differentiation of this space, of course, as you can see. Another algorithm that is very easy is the key nearest. As the words say, so nearest, I actually classify my dots, my new items, watching what is the nearer other point. So in this case, you have this area. This blue area means that in this area, if I put a point, the nearer one will be blue. And so the new point will be a blue one. As you can see, we can have fine, medium, of course, k and n. It means that fine and k equals to 1. Not matrix, sorry. So we have to convert from 2D array matrix to 1D vector. That is the main purpose. And of course, we have to add the label to all the images that we train. So, as you can see here, we have the first part of the code that is easily a choice of the size that we want to use. After that, there are some codes that I don't want to explain you, but it is very simple. I actually go in the directory of false image, and I extract with a for cycle of all of the images. I read the image with the image read command. Okay. So once I read it, I resize it with image resize here. Resizing it, but also I want to make it also all grayscale. So this is only a check. If the image is not grayscale, like you can see here, if the size of the image is not 3D, I make it gray with this very easy command. After that, this is the main part. I put in this array image false the vector corresponding to the image. As you can see, double image is actually a matrix, but with this command double dot, I can convert in matrix in a linear vector, and I put it one above each other in a matrix that is called image false. After that, I put zeros, that means false in our language, at the end of each image. I perform the same computation for the true image here, and this time I have to put ones at the end of the image because of 2 is classified as 1 in our case. Once I've done it, I of course merge the two parts. So I take the true part and the false part, and I put it once above the other. This is only a command to clear all variables except this one. I want to show you the results of this computation. Okay, this is our final matrix. As you can see, all the rows are one and a different image. So one is the first image, and all the columns are the pixels of the image starting from the top left corner. Of course, if we use a 50 per 50 image, we will have 250 to 20,500 columns of pixel. And here we have the label. As you can see, in the last columns we have ones for the first image, and if we go deeper, we have 0 that are the first image. So once we have this, we can actually perform our training process. So we open classification learner, this one. Here we have our workspace. We start a new session with this on the top left. Starting the session, the MATLAB already understands what is the variable that you want to use, because in this case we have only one correct values. As you can see, we import EMG, that is a matrix, and we have to set something before starting actually. Of course, we have to use columns as variables. In fact, we have decided that each columns represent each 1 pixel of each image, so our characteristics of the image. And we set the response, so the label of our image, that is actually the last columns. This is particularly important, the cross-validation. As Alberto said before, we have to divide our data in some more little data set that make us able to perform a validation on our training actually, because otherwise we can't be sure if our computation is going well or not. In this case, each 5 folds, so we divided our image in folds of some size that we can set. Each 5 folds, I stop my training process and I perform a validation. So I don't longer train my net, I put the image of the validation set inside my training net, and I check if the label that I know, because I know the image, is the correct label, that is the predicted label or not. If yes, I'm performing a good training process. If not, of course not. I can start the session. Okay, it will take some time because it's a very complex data set in this case. Okay, let's start from this graph. Before I show you a similar graph with 2 different characteristics, but it was better than this. I mean, here we have a lot of points that aren't divided into different, very clear spatial representation. We have blue points over orange one, so it's not so easy to understand. But why? You have to understand that this is the plot of column 1 and column 2. So we have actually plotting the first 2 characteristics, the first and the second pixel. So each point is an image. If it's blue, it means that there is no car. If it is orange, it means that there is car. And each image, of course, collocated in this special representation according to the first and the second pixel. In this case, as you can see, we haven't a correlation between the images. Of course, because the first and second pixel on the top left of an image don't tell us anything about if there is a car or not. It probably is only a background or not interesting data. Here we can choose all of the algorithms that we want to use. So we can start with the linear discriminant. I start the training to show you how it works. Starting the training, it takes some time and will give us results. So speaking about this, it is important to understand a thing that we understand the content of the image because we have a spatial representation of the image. I mean that the pixels that are near, the pixels that represent the actual car inside the image is meaningful because are near one of each other. So if I see the image in its I can see the car inside, for example. But if I flat this image in a vector, as you can probably understand, I lost this spatial representation. So I lost the collocation of the pixel and all of the information that is carried with this spatial representation. So for this reason, as you can, you will see in a few moments, this is not a very powerful training process, because with machine learning we lost the spatial representation. Actually, with neural network that I will show you in a few minutes, we will keep this spatial representation, so we will see the image of the car inside actually of the actual image. It's very long, but okay, we get 65% is not so good. I bet you can understand that if we have a 65 accuracy, if you deploy a software like this, we will kill someone in the crossroad. So it's not good at all. We can perform also KNN. As you can see, we can perform fine KNN, medium KNN. Of course, we perform fine KNN only for a matter of time. We train it. But you will see that also in this case, the accuracy isn't good at all. Only because of this reason. It's not that machine learning is worse than deep learning. Deep learning sounds better than machine learning, but it's not best in every case. In this case, it's best only because if in one case we lost the representation of the image, in the other we keep it. Is like I say, you understand if there is a car on an image or on a vector of pixel one after each other. I bet that you can't understand if there is a car in this vector or not. This is the same for the machine learning algorithm. We will wait some time. If you have some question, this is the best time to ask. No question.
Daniel, like one general question. I mean, you said that at the beginning, machine learning, deep learning is very useful because you can reach an accuracy that is better than humans. Then you said that while you label your data set, you look at the image and then you say, okay, that's a car or that's a. So you are, like, I'm thinking that you are introducing in your data set a human error, so that the model will not be better than you.
Yeah, yeah, it's a right question. Of course, you introduce the human error, but you introduce the human error in labeling. It is different from the error that the net will get. I mean that, of course, if you are wrong in label the image, you make some mistake. This data set will be not correct, of course, is very clear. But once you feed the net with this image, the net understands if there is, if there is one image on all of the other that is wrongly labeled, the net understands that this is not so important. It's only one on lots of other images that are correctly labeled. It is important because machine learning is I can see a strength of machine learning or deep learning is this topic. In fact, can abstract the underlying patterns that are in image and so classify the other image correctly. So if you make some mistake, probably the net, if it is correctly created, will understand and will understand the correct image, not the wrong. So it's not the wrong image. And as you can see, KNN perform 76%, but is not enough for our purpose. So we see that machine learning in this case can be useful. We can get through the deep learning approach. Okay. deep learning approach. As Alberto introduced you before, deep learning is a complete... Yeah, of course.
I'm still not sure what the two values on the x-axis and the y-axis mean. I understand that the color means if it's a car or not a car.
Okay.
But what does the, was it like, what is it 0.2 and 0.8?
I explain you. So you get it that there are some features in each object that classify it as the object. Like I mean a car, a wheel is a feature that classifies this image like a car. Also humans works like this. I can understand if it is a car if I see wheels, the color of the car, the shape of the car, and so on. The machine learning performs in the same way, but with values. So, if in the other most easy case we have a characteristic like the size or maybe the color that are more clear to see, in this case we have the value of each pixel. So, you can see the image like a series, a matrix of values. Each values represent the magnitude of the intensity of the color in this point. So here we have each point is an image, and the two columns, this one is the first and the second column, represent the first and the second pixel. So in this case, this image will have the first pixel, column 1, with a value of 0.50 something, and the second pixel with a value of 0.35, for example. As I said you before, this is not very easy to understand because of clearly if there is a car or not in an image, we can see it from the first two pixels. It's not a meaningful characteristic. You got it?
Yeah. Is there a way to show other pixels? Like this is just about those two pixels.
Okay.
I suppose that now I'm to make the classification for all the pixels.
Yeah. Of course, MATLAB classifies all of the pixels. I will show you what I mean. Here, of course, we live in a 3D space, so we can compute a multidimensional plotting. So MATLAB performs 2D plotting once, but you can see here in this side that you can choose the columns. So if, for example, I want to see the link between, I don't know, the 20th pixel with the 21, you can see that I will have this representation. Unfortunately, in this case, that is a multidimensional case, I can see the correlation of all the characteristics with the other all characteristics. Of course, if I choose the same column, I will have a rect. Is I think clear because all of the pixels correspond to each other. So it's okay. Perfect. We can continue.
Vai, prova a metterlo.
Okay.
Prova con nulla. No.
Now we can show. We have to see how the deep learning approach is computed. As Alberto explained you before, deep learning. In this step, our deep learning net will understand how to recognize a wheel from our complete image. It is quite magic, but actually it works because the deep learning net trains itself, and if you see each layer at the end, you can actually see that it recognizes actually the most important feature of the image. I will show you in a moment. And this last step, it is needed to classify this feature into our objective, of course, because I don't want to understand if there is a wheel in an image or there is something else, but I want to understand if it is a car or not. So this last part will do this work. This is a short video to introduce you into the convolutional layer and so on.
after that I will explain.
Classical neural networks pass vectors of values from layer to layer. Basically, each node takes in a set of numbers and produces a single number as output. However, when working with images, spatial structure is important. We can't just unroll the image into a list of numbers because neighboring pixels are related. To preserve that spatial structure in a convolutional neural network, a node will take in a set of images as inputs and produce one image as its output. So at the layer level, a set of 2D arrays goes in and a set of 2D arrays comes out. But what does a convolutional layer do? What is convolution? Starting with the raw image, a convolutional network breaks the image down into features. This is typically done using multiple sets of layers, and the first layer in each set is a convolutional layer, which detects specific patterns in the images passed to it. Imagine making a light filter that lets more or less light through in a particular pattern, such as a vertical stripe. If you held this filter over a part of an image that had a vertical stripe, the filter would match the image and a lot of light would get through. But if you held it over an area that didn't match that pattern, most of the light would be blocked. Moving the filter all around the image would create another image that was bright where the original image matched the filter pattern and darker elsewhere. This is what the nodes in a convolutional layer do. Each node has a particular filter, which is an array representing a specific pattern. Place the filter in the top left corner of the image. The filter is usually much smaller than the input image, so it covers just a small portion of the image. Multiply the pixel values of the image in the filter, and then add the result. This gives you a value that you can interpret as how closely that small piece of the image matches the pattern of the filter. Move the filter over and repeat. Keep going until you move the filter all the way to the bottom right corner. The mathematical operation you've just performed is called a convolution. Because you get a value for each position, the result is a new two-dimensional image, the activation, which highlights the presence of a particular pattern in the input image. Because each node in the convolutional layer has its own filter, the layer takes a given input image and returns a set of new images, one for each filter. You can think of each node as performing the job of detecting a particular feature in the input image. What feature the node detects is determined by its filter. Remember that the filters are the parameters for that layer, so they're learned during the training process. In this way, convolutional networks learn both what features to detect and how to use them to classify the image.
So, as you can see, there is the main core of the deep learning net, a deep learning net, is the convolutional filter, the convolutional layer. Now I try to explain you how it works, but the video already introduced you some notation. So here we have the easiest structure for a deep learning net. As you can see, we have a different layer here, and now we will analyze one layer for each one to get how it works and what is its purpose. First of all, image input, I think, is very easy to understand. It takes an image and it normalizes it, because we need normalized data to work, of course. We need normalized data, actually. The first step is convolution, that is the core, as I said you before. So, what is a convolution? It's an easy mathematical process where you can, you take a filter, like this one, a matrix. A filter is actually a matrix. You multiply element-wise, so element per element, each first one to the first one, and so on. So this first filter multiplied by these values and add these values to get a final result here. So in this case, we have a vertical edge detection. Why it is a vertical edge detection? Because, as you can probably understand, with 1 in this position and -1 in this, if you multiply this in this section, If there is a discontinuity in the image, so we have a rapid change of values of the pixel, it means that there is a border, there is a vertical edge. And so in this case, if there will be a vertical edge, we will have a very high values. So a very high values means that in this particular point there is the feature that I selected. So now I want to get this particular answer. In fact, filter is have different characteristics. So size, in this case 3 by 3, but also the values inside the filter. Actually, the values inside the filter are the parameters that the training algorithm will set during the net. So you don't need to create each filter from each one to extract the feature, but the training algorithm will do it for you to best fit your problem. And after that, there are lots of other parameters called hyperparameters that are filter parameters that you have to set before the training algorithm. So you decide before, and after that we perform the training. For example, the size of the filter, the number of the filter that you will use in your net, and of course also how it moves along the image. You can choose a faster moving or slower one, but it of course in this case. So how it works? We take the first filter. Okay. We wait. Okay. Actually, it's working very well. Okay. As you can see, we multiply each filter. We move it along the image. We multiply it, and we create a smallest matrix of values, as you can see. This is the first filter. Of course, normally in a convolutional layer, there are lots of filters, like, I don't know, 50 filters. So each filter is multiplied by the matrix. As you can see, it's the same process. With different result, of course, because it's a different filter. Once we've done this process for every filter we have decided to use, we get a new matrix, like this one. So here we have the characteristic. First of all, the number of filters. We can decide each convolution layer to use a different number of filters. The filter size, the stride, that is the movement along the image, so I can decide how move inside the image. And the zero padding, that is a small area that I can exclude from my from use. So the filter will start from this corner. Once I've done it, I will get lots of new matrix. So you have to get that from one image. If I use 50 filter, I get 50 matrix. So it's a very enlargement of the problem. I can't continue the performing of my algorithm with 50 matrix. It will increase and increase exponentially, and making it impossible, of course. So I have to introduce some layer that will reduce the complexity of my network. In this case, we have the first one, that is the review layer. It is a very simple activation function. If pixels are negative, I take it to 0. If are positive, I take this value with the max from 0 to x. Of course, it is important because images can be characterized by negative pixel. What is a negative pixel value of this? So we eliminate all of the negative values that are created by the convolution. After that, as I said to you before, I have to perform a downsampling. I take my matrix and I downsample it. So I take some type of convolution pooling, like this one is the max pooling. I take the max pixel, the maximum pixel in this area, and I take it, this one for this, and so on. So as you can see, I get a final
matrix that is very with a less size than the first one. This is the average. It works at the same time. The dropout that Alberto introduced you before is a layer that excludes some nodes in a very in casual way. So it is important because if I get too much in details in my image, for example, let's assume I have lots of images of cars that are red, and my net, if it's very detailed, will extract that the red is a feature that identifies a car, but it's not true. It means that if I give the net a red phone, it will give me true as label, but I don't want this behavior. So I drop out some nodes that are too specific, and I do this with the dropout layer. I know it's maybe complex to understand, but it works, and it eliminates lots of error in this way. And the last three layers are the fully connected layer. What is the fully connected is important because if I have, for example, 100 features that identify a car, I don't want to get 100 different responses. So my output from my net will be, is a car or not? I don't want, if there is a wheel, there is I don't know, the shape of the car, there is something else. I want to know only the classification. So I collect all of this information into two nodes. There is a car or not with this fully connected layer. Softmax is only a normalization, and class output assign each node with this label. Like you can see here we have flower, couple, and so on, with the probability of corresponding label. So this is the toolbox that we will use in a moment. It is called Deep Network Designer. It is built in MATLAB, and it gives you the possibility to build your net in a graphical way that is not so common. You can build the net taking the block from here, putting it in here, and link one to each other. Once you have all of your design of the final net, you export this to the MATLAB environment, and you perform the training. Of course, maybe a question can be, but how I can design well my network? But it is not a certain field, so there are lots of theories on what is best or worst, but you have to use your, I don't know, your imagination. You can design your network as you want. You can try it. If it works, well. If not, you are a bad designer of network. You will change your work. I don't know. And so let's see the demo of deep learning. Much easier than the previous one, much shorter. First of all, like in the other case, we have the preprocessing. So we import the image with this dimension, and this is the most important command. Image data store, create a data store that you have already seen before, with image, that is the folder where the image is. This is the command label source that gives you the possibility to assign each image some label. So in this case, we take the label from the folder names. As you can see here, the image is divided into folder and false folder. So all of the images that are in two folder will be assigned to, and the other image in false will be false one. So once you have imported it in this case, you split our data set, as I said to you before, this is very important, into a training set that take, as you can see here, the 80% of all of the image, a validation set that is the 10%, and the remaining part is the test set that is the last. Once we have done it, so we can run this code. Actually, it is very fast, because as Alberto said, we don't import all of the images inside the Marta workspace. We have a deep network designer. Now, we haven't time to design a network now, but it's very easy actually. We can import, perfect. We have to load this. We have these net point math that are 3 different net already designed. We can double click on it and import into the workspace. Now, if I go into the deep network design, I can import it to see how it is the behavior. The first one is the 30-layer workspace. As you can see, we have a 13-layer net with 2 convolutional layers. This is the first convolutional layer, this is the second one. And these are the other layers that are needed, as I explained to you before. This is the dropout that now is set to 0, so it won't perform dropout at all, and so on. Fully connected, softmax, and classification output. If we import the other one, that is much more complex, it has 4 convolutional layers. As you can see, it's difficult to see each layer, but you can zoom, of course, you can zoom. And you have to set all of the hyperparameters here. As you can see, like I said before, if I click on a convolutional layer, I can see the name, of course, the size of the filter that I have to decide before, the number of the filter, the stride, and so on. All of these parameters that I have to set before. Once I have done it, I can perform an analyzation. Analyzing the network means that I check if it is coherent. So if the input of each layer correspond to the output of the previous one. It's only a size comparison. So as you can see here, we have the activation, so the parameters. Learnables means parameters. In this case, we have these parameters to learn from the net. We have 21 layers, 0 warning, 0 error, so our net is coherent. It doesn't mean that perform well, actually. It is only designed well in this case. So after that, we will perform the training, the actual training. We set the training option here. So the Adam algorithm, the initial learn rate, that is the step. Initial learn rate, you can see initial learn rate and as how fast and aggressively I change the parameter if I goes wrong. So I put an image on the training process. The image is not, the trainer don't perform well, so I don't classify it well. If I have an high initial learn rate, I change a lot of parameters. So the risk in this case is to do some damage on the training process. Also, I want to see the training process and so on. But of course, I can train the net right now because it will take like 30 minutes. So we have done it at home, and we okay, lots of folders. Here we have, for example, a training of the first most easy net. It is speed up, of course, it is not so fast. As you can see, the blue lines represent the accuracy, the black dot represent the validation. So each 10 step, I perform a validation. I stop my training and I feed the net with my data set. If the black dot accuracy is higher, it's good. Here I have an accuracy better in the other data than in mice. It is lower, it is not good. In this case, as you can see, the net is very, very less powerful, not too much powerful. In fact, we can see that it reached 80% of accuracy, but it is not so easy to get over it. This is because with only 2 convolutional layers, it is difficult to understand all of the features that we need to classify a car. In fact, as you can see at the end, I speed up it. As you can see, we reach only the 85%, as you can see here. And as you can see also the loss, okay, as you can see the loss also is not, is 10 to 0, but very, very slow. If we see, for example, the convolutional, the 4 convolutional net, so the most complex one, as you can see, it started to become more and more powerful. But there is a problem at some time. In fact, we have not so much data set. So, as you can see here, in this point, I hope you see it, the validation set, the loss of the validation set is higher than the other one. Here, I don't know why, the validation set is higher than one. What does it mean? That in the training set, I perform very well. As you can see, like 100%, so my training image are recognized 100% right. But if I give it another image to classify, it don't perform so well. It doesn't perform so well. It means that we lack of generalization. We understand too well our image, like a kid that you give it 10 images of a car and understand that they are image of a car, but if you give him another image that represents a car, maybe it tells you that it's not a car because he never see that image before. And this is the problem, the overfitting problem that I spoke to you about before. To solve it, we can use a more efficient net, the last one, this one, that we increase the data set, we double the number of images, and we introduce the dropout layer, as I said to you before. As you can see, the training is performing very well, and as you will see, we have the validation set that is actually coherent with our data. So in this case, we have an accuracy that corresponds to the 100%, both in validation and in trace. So it's very good. Also in loss function, we have here loss that is equal in validation set and is trace. This means that our training is being computed well, and in particular that our net is able to understand new images that haven't seen before. So this is the ideal situation. Of course, this is not always true. For example, maybe this net is too complex for your application. Maybe your hardware is not able to compute this type of net, so you need a lighter net, maybe not so good, but that perform well in other cases. So we reach the end of this section. The next step will be, this is the first image on our work in progress. We will build an actual model of our CROSSROADS. This is my best car, and we will deploy the algorithm to actually try if our net will work on a real solution. This will be done in the next seminar, of course, with the simulated coding of the traffic. So, on the traffic light management, we will code how to change the LEDs that represent the traffic lights. we integrate our net that we are designed today to understand if there is a car in some way, and we deploy it on Arduino. So you will see also the deployment on hardware. Now I give the word to my colleague that give you another some information on transfer learning and the conclusion of this lesson.
Let's talk about transfer learning in, let's say, a fast way to understand what it is, and then go to the conclusion. Okay, let's start. What do you mean transfer learning? We start from a network that is already being prepared and trained, so we have already functioning network. So we have loaded pre-trained network. Okay. A network are called the effect, okay? Then we take this and we substitute the last part, so the classification part. It means that all the feature extraction of the network will be the same as the previous one, but we take the classification, so the layer that does the connection between the features and the label, and we change it. How we change it? We do a new training, we have a new training images, and we do the train option. Of course, this is a smart way because we no longer have to train all the parameters, but only the one needs for the classification. So we don't need such big data set to perform a good network, but we need only less of them, like in this case, 1,000 images. Okay. And then with this, we have to predict and assess. So we have the training network. We have I can say the general network. We specialize the classification network. Then we have the network, the new network, ready to use with the test images. With this, we can deploy the result, so we can see if the image is labeled correctly or not. In this case, we have a both, of course, and this is the other, but as you can see here, it's only, it classifies right, it's a both. Okay? This means the network is working. Sorry if I go so fast, but we have a little bit in hurry. So, it's clear. We start from a network, we change the classification layer, so the last part, with a new training, but a lighter training that the one we should have if we classify all the network. And then we have a network that is functioning very well on the new images. Okay. So, what it means in practice? We can see here performance and training. If we use this approach, we start from an higher point. So we no longer start from zero, but we start from something that does work. And when we perform a steeper curve of learning, so we learn better. And then we go to an higher asymptote. Of course, if our, as you see before, the network that we build arrive to the 100%, okay, no problem. In a general way, we can say that the transfer learning will achieve a better, higher performance. Of course, this with this approach, we have the back side of our coin. So we have higher complexity, because let us assume that we want to use transfer learning on AlexNet. AlexNet is the pre-training network of MATLAB. Okay. This is a 25-layer network, so a bigger deep learning network. So for an easy task, it could be too much. So we have to deal with a more complex structure. We have a more complex network. This is the minus point of this approach. Okay. And then we can go to the conclusion. About conclusion, let's start. We have this, a little recap. with this table and see the various steps that we take today. The perceptron needs is, of course, these two are machine learning. Needs vector. They are fast, but in the general, you can say the general cons is that we don't get all the information to the 2D array of an image, but we only give a vector, so we can say lose some information. Then we can go to the convolution. Convolution needs metrics, and it's powerful, yes, but has a higher complexity and needs a lot of power to be calculated. So we can use some add-on, such as the dropout, or we can use the radius, so some other layer, intermediate layer that can reduce the dimension of our network. And then, last one, we can use transfer learning. Okay. So we have an higher accuracy, but it's not optimized. I mean, no, you generally use a bigger network than the one required. Then we can. You may ask, why use MATLAB? There's also Python, other stuff that can do the same. But well, let's see some pros. We can use a user-friendly interface. We can use the integrate with the other functions. So the classical environment that you already know. So all the functions of MATLAB can be used also in deep learning, and deep learning can also use beside the other function. So it's all correlated. Then we have, as you can see, specific app with a design to design our net and see it graphically. So it's user-friendly again. And also the training spectrum here, we can say the picture of the validation and the loss. So it's clear and smart to understand. And then, of course, this is the part that we will speak about next seminary. So the integration with Simulink. So no spoiler, but we will integrate deep learning with Simulink. Okay, and then we can speak about. I need to connect MATLAB and I know well. There's another slide. There's the best approach to every type of user. If you are a beginner, well, it should be cool to use the graphical toolbox and use maybe a transfer learning to achieve easily an high accuracy in your network. And moreover, if you are an intermediate, you can longer use graphical toolbox, but you want maybe to start training your own network. So it's again you can use MATLAB in another way. And then last, if you are advanced, you maybe prefer to use code, or you can use you want to import a library from other can say framework, such as Keras library, a very famous library in Python. So we can use this one inside MATLAB. Okay, so since now you don't see any type of code, but all this stuff can be done by coding. We show you the graphical toolbox only for a teaching purpose, okay? And then, so this is the approach for the 3 steps. We can see the interoperability of MATLAB. This is called on-NX, so it's a format of network that can, it's like a shared between the different platforms and frameworks. So maybe you have already heard about TensorFlow, that is one of the most famous one using Python. It can import and export file on XX, on NX. You understand? And the same for MATLAB, the same from the other frameworks. Of course, this is a very smart way because you can integrate your network with other people that can use other type of networks. Okay, now let's start the competition to win our beautiful gadget. And then pizza for everyone. So stay here And please go to socrative.com, also with your smartphone or tablet or what you prefer. Then click on student login, and then the room MATLAB for me. And then let's start the challenge. Please enjoy it.